We're going to now begin using energy to actually do some problem solving. So there's a few things we want to think about when we are using energy to do problem solving. And really the key is we're going to focus on the transfer of energy. Okay, similar to what we were doing with those energy bar charts, except now we're going to do it in equation form. So we want to think about what kind of energy does the object start with. That's the first question we want to ask. What energy does it end with, all right, at some later point in time? Okay, and is there any work being done by non-conservative forces? All right, and we're going to bring that all together using our equation. It's essentially the same idea as what we were doing with the energy bar charts, but now we're going to use this equation. The one thing you want to keep in mind is we do want to be careful with the sign of our work. Make sure that the sign of your work makes sense logically. If it's gaining energy, we should have positive work, and if it's losing energy, there should be negative work. So here's the first practice problem, and the first thing I'm actually going to do, we have this nice diagram here, is I'm going to go ahead and think about what kind of energy I have at each of these points in time. So initially we have a spring being compressed at point A here, so I'm going to start with US, our spring potential energy. It then goes up to a height where it momentarily comes to rest here at point B, so that's going to be gravitational potential. Now there is some kinetic in between. We're going to find out in a second that that actually doesn't matter. And then we get to the end here at point C, and we have a height, so we're going to have gravitational potential, and we are moving, so we also have kinetic. So for that first question, we want to calculate the height at point B. I'm going to start with my conservation of energy equation, E initial plus work equals E final. And I'm going to go ahead and fill in the things that I know. This is going to be similar to our F equals ma equations, where you have to fill in the specific energies that exist at various points in time. So we're starting here with US, spring potential energy. That's the only energy we have initially. There is no work being done, so I'm just going to skip that part. And the energy we end with at point B here is gravitational potential energy. So I've plugged in the formulas I know for each of those, for spring potential energy and gravitational potential energy, and now we can go ahead and plug in the values I know. My spring constant is 600. X, the distance the spring is stretched, is 28 centimeters, or 0.28 meters, okay? And that's going to be equal to my mass, which I know is 1.2 times 9.8 times my height. And when I go ahead and solve for that height there, I get 2 meters as my height. For the second question, I want to know the velocity at point C. So once again, I'm going to think about my conservation of energy equation, E initial plus work equals E final. And for this one, I'm going to just think about going from point B to point C. There are a few different ways of doing this, and I'll actually show you a different way in a second. But if I'm thinking about going from point B, I'm starting with gravitational potential energy at point B. There's no work being done. And I end with gravitational potential and kinetic at point C. So I can go ahead and fill in those formulas once again for gravitational potential energy and kinetic energy. The one thing I'm going to do is I'm going to say this is HI, my initial height at point B, and this is HF, my final height at point C. I now can plug in what I know, so 1.2 times 9.8 times 2 equals 1.2 times 9.8 times 1 plus 1/2 times my mass, which is 1.2, times v squared, and when I solve for v, I get an answer here, 4.43 meters per second. So that's going to be my velocity at point A. I also could have set this up considering the period from A all the way to C, okay? And so for that, I would have said that I start with spring potential energy, and that just becomes gravitational potential and kinetic. So we're going from point A here all the way to point C, all right? Whereas with this one, I just went from point B to point C. Either one is valid because as long as we account for all the energy that an object has at one point in time, in this case point A, and all the energy it has at a later point in time, point C, and we account for any work done in between, which in this case was 0, okay, this equation is going to work, right? So as long as you account for all the initial energy, all the final energy, and any work done in between, it doesn't matter what 2 points in time you pick. For the last part of this problem here, we're asked to draw an energy bar chart showing the energy at these various points. So I'm going to start here. I have spring potential energy at point A. Okay, that's the only energy I have because we're not moving. Going from A to B, there's no work being done because there's no non-conservative forces. And so all of that energy that was spring potential energy at A becomes gravitational potential at B. Once again, no work done between B and C, and what I'm left with is half as much gravitational potential energy. And I know that because my height here was 2 meters, and my height here is 1, so I'll say it's 2 bars of gravitational potential, and the rest has become kinetic. For this next one, we have a situation where there's a ramp, okay, that has a length here of 4 meters, and it's sloped at an angle of 30 degrees. And we're going to put a box here with a mass of 5 kilograms at the top of that ramp, all right? And it's going to slide down the ramp, and as it's sliding down, there's a frictional force opposing its motion of 10 newtons. So energy-wise, I want to think about what kind of energy we start with, what kind of energy we end with. So we're starting up here with gravitational potential energy because we have some height. We don't know what it is, but we do have some height above the ground. We're ending here with kinetic, okay, because we're moving and we no longer have a height. And there is some work done by friction that's happening in between. So I'm going to go ahead and think about my conservation of energy equation here, E initial plus work equals E final. So that initial gravitational potential energy plus the work done by friction, I realize that work will ultimately be negative, but the cosine of theta term will take care of that. So I'm just going to add in the work done by friction even though that work has a negative value. And that's going to be equal to my final kinetic energy. So I can go ahead and fill in the formulas I have for potential energy, work, and kinetic energy, and then start filling in the values I know. So I know my mass here is 5, G is 9.8. My height I don't know, but I can think about this triangle here. We have a 4-meter long ramp sloped at an angle of 30 degrees, and so this height here is just the opposite side. So I can say that height is just going to be 4 times sine of 30, which gives me a height of 2 meters. So I can fill in that height there. I'm then going to add the work done by friction, so that's going to be the force of friction, which is 10, times my displacement, which is 4. And I'm using that full distance because friction acts as that box slides that entire displacement. So the displacement should be 4, not 2. My angle here is going to be 180 degrees because as I'm traveling down the ramp like this, friction is going up the ramp in the complete opposite direction. Okay, so the angle between my force and my displacement is 180 degrees. And that's going to be equal to 1/2 times my mass here times v squared. So I go ahead and I solve that left side, and I end up getting 58 as my number there. Keep in mind you should be in degrees mode, and that's going to be equal to 2.5 v squared. And so I find that my velocity here is 4.8 meters per second. So let's talk about this idea for a second. We just did the exact same problem 2 different ways, one time using energy, one time using forces and kinematics. Both of them are okay, both of them are physically correct, both of them are valid. However, my advice to you, it is almost always easier to solve for things using energy. And this problem wasn't that bad, dealing with forces and kinematics, but I still think even this problem was easier using that first method with energy. There's less work involved typically. Okay, no pun intended there. But I think it's almost always easier to solve using energy. There are 2 major situations when we can't use energy. The first is time, okay? Energy doesn't take into account the time piece of any of these. So if you need to know something about the time, you're going to have to use forces and kinematics. The other one is when you're solving for things at angles, okay? Energy is a scalar. When we want to know angles, like for projectile motion, for example, okay, we can't use energy because energy is just going to output another scalar answer. Right? And it's not going to allow us to determine the direction that something's moving or accelerating or things like that. So those are the 2 big situations when you really can't use energy. But in most other situations, if you can use energy, I would suggest trying to use energy.